Okay, good afternoon, everybody. Today is our seventh lecture, discontinuous solutions of the Euler equations, shock waves, and contact surfaces or contact discontinuities. So first of all, I'd like to explain why we're going to discuss these topics and what is the relationship of this topic with our previous lectures. So last time, on previous lecture, we considered finite volume method for linear direction equation and also for 1D Euler equations. So I'd like to remind you. So the idea is that we need to build our numerical method starting with the integral form of Euler equations. That's because we need to find so-called weak solutions and discontinuous solutions, and that is why we start with integral form for Euler equations. And the idea was that we should apply this integral form of Euler equations to compute cell averages of our grid function in computational cell. So we should here A and B are just arbitrarily 2 points on axis, and T1 and T2 are just 2 arbitrary time instants. And let's choose A and B as the boundaries of our computational cell, xm minus 1/2, xm plus 1/2, and T1 and T2 time instant, Tn and Tn plus 1. That is current time layer and the next time layer. And so we just formally use apply this formula to our computational cell, and then we should introduce U, the capital Mn, is the cell average of our function U. So this is the object of interest. So we would like to find these average values within during our simulations. And in the same manner, we obtain these objects Fn plus 1/2 n. So some approximation to the average flux along this edge of our computational cell. And the question is how to compute this numerical flux. How can we approximate this numerical flux? And so this is the common formula of the finite volume method. And the idea is that this numerical flux F is a function of 2 states. So if we need to compute the numerical flux through this H, it depends on parameters to the left of this H and to the right, UMN and UM plus 1n. That's the idea of the finite volume method. And we discussed the transition and the coupling of this numerical method with the fundamental problem for the Euler equations. So okay, we need to compute the numerical flux through this boundary between UMN and UM plus 1. Let's forget at the moment about numerical method, numerical solution, and consider this problem as just the Cauchy problem for the Euler equations. So we have our Euler equations, and we need to compute the following Cauchy problem with the discontinuity in the initial data. So consider the initial data in the following form: U equals UL if x is less than 0, and U equals UR if x is greater than 0. So it means that for x equals 0, we have a discontinuity, and UL and UR are just constant parameters. So U is conservative variables vector, so U sub L means rho V, rho E to the left, and so UR to the right. And generally speaking, there is no any relationship between UL and UR, so they can be just arbitrarily. And the idea is that if we know how to solve this problem, so how to what the solution will be, we can say that okay, but here we can apply the solution here and consider that UMN is the left state and UM plus 1n is right state, and we need to know the solution at x equals 0, that is between at the boundary. So if we know the solution at any time instant, we will take it for Tn plus 1, so at the next time level, and then we will get the the numerical flux from the solution of this Riemann problem. And if we will take the solution exactly, we will get the Godunov method. We will discuss it later. If we compute this solution of Riemann problem using some approximate approach, we will get so-called approximate Riemann solver and so on. But this is the idea. So if we want to know how to compute accurately numerical flux, we should know how to solve this problem. That is why the next two lectures will be not about the numerical methods itself, but it will be the solution of this problem, because the solution of this problem is in close connection with the numerical method, with the finite volume method. And there are a number of ingredients for the solution of Riemann problem for hyperbolic equations. And what are they? So the structured solution of the Riemann problem. I'm not going to discuss with mathematically rigorous definitions of this topic. So for sure it should be, but actually so there should be some balance between practical needs and mathematically rigorous statements. Anyway, so there are the following items that indicate the structure of the Riemann problem solution. In the input data of the Riemann problem, there are no parameters with the dimensions of length or time. Therefore, the desired solution is self-similar. So what does it mean, self-similar solution? It means that our solution, u of xt, actually is not of xt independently. So our solution should depend on a variable xi equals x over t. So the solution, if self-similar, is if it looks, so I'd like to show the picture here. So this is the exact solution of so-called solved problem. We will also consider it many times later. So it's one of famous benchmarks that is used for verification of implementation of your numerical method. So it follows the paper. Sot is a surname, so it's Gary Sot. It's just an author who published a paper in the Journal of Computational Physics. And he considered so he just took some parameters to the left, and to the right, and compared a number of numerical methods for just one specific Riemann problem. And after that, almost all people, many people who develop their own numerical methods or who just implement them and who would like to check if the implementation is correct, they took these parameters from the paper of Sot and compare the numerical results, not with his results, but with the exact solution, because it's possible to get the exact solution. So he considered the Riemann problem with the following parameters. For example, the density of gas is equal to 1 to the left of x equals 0.5 and to 0.125 to the right, for example. So this is the initial state. And how this exact solution will look like. So after some time, we'll get the following structure. Looking ahead, so this is the shock wave, this is a contact discontinuity, and this is the refraction wave. So we're going to discuss all the structures. So today we are going to discuss these two structures. And what does it mean that the solution is self-similar? It means that at the next time instant, we will still have this shock wave, refraction wave and contact discontinuity. It means that the solution will keep its structure, but only stretching in time. The next time instant, the shock wave will move, the contact discontinuity will move the head and tail of the refraction wave will move, but actually the solution will keep its structure. So it means that the solution is self-similar. So the solution of the Riemann problem should be self-similar. It means that it should have the structure like this one. It is known that the class of self-similar solutions to the Euler equations consists of constant solutions, including those connected through a discontinuity, either contact or shock wave, as well as refraction waves. So this is the illustration. So the illustration of a self-similar solution. So consists of constant solutions. So this is constant solution, this is constant solution, and they're connected through either a shock wave or a contact discontinuity or refraction waves, continuous solutions of the Euler equations. And no more than one shock or refraction wave can propagate in each direction from the discontinuity. So it means that if you have discontinuity here, that we have only one shock wave propagating to the right and one refraction wave, for example, to the left, or quite contrary. But we cannot have two shock waves propagating to the same side from contact discontinuity. It can be proved. Maybe we will do it, but actually that's not too difficult. But the most important thing to know the final result, that the structure of the Riemann problem solution should be like on this picture. So one more time, the self-similar solution means that we have such changing in time, variation in time of our solution. Usually in books you can meet the following pictures. So the structure solution of the Riemann problem. So what does it mean? So suppose we have one more time, that's not about numerical solution at all. So we just consider our Euler equations, and along x-axis we don't have boundaries and so on. And so initially for x equals 0, we have discontinuity in all variables. I mean velocity, density, and pressure. Some parameters to the left and some parameters to the right. For example, the closest analog from real life is a shock tube. So maybe so shock tube is a device to produce shock waves to get some high pressures. For example, if for some applications you need high pressure, so shock wave is a mean how can we get the high pressures. It means that we can take just a long enough tube, and so in one part of the tube we can pump the gas with high pressure, and then we have a diaphragm, and then it should be ruptured, and then this high compressed gas produces some disturbances that will propagate to the chamber, low pressure chamber. So it will propagate in the form of shock wave, and after that there will be a contact discontinuity, and the refraction wave will propagate through the high pressure chamber, and so on. The possible cases for the Riemann problem are as follows. So we can have one of four possible configurations. The SW means shock wave, CW means contact wave or contact discontinuity. So it means that we can have a shock wave that will propagate to the right relative to contact discontinuity, and the shock wave that will propagate to the left. Or we can have a shock wave that will propagate to the right and a refraction wave that will propagate to the left. So this is a case that was illustrated here. So we have a contact wave, we have a shock wave, and we have a refraction wave. So a refraction wave is a continuous solution. That is why it is shown here like a number of blue lines. And the shock wave in Euler equations is a structure without any thickness, so it's infinitely thin, just a line structure. That is why it is depicted as a line, and the refraction waves. So it's called a fan of a refraction wave. Or quite contrary, we can have a shock wave that will propagate to the left and a refraction wave that will propagate to the right. I understand that maybe at this point you may not understand in detail, so what does it mean? But we will go back to this picture several times, and each next time you will get more and more understanding of the structure of the Riemann problem solution. Or we can have two refraction waves. So one refraction wave will propagate to the right and one to the left. The whole picture can be, so it can be rotated. For example, parameters can be different, and for example, maybe all waves can propagate to one direction. But what is important, relative to contact wave, we will have only one wave propagating to the left, one to the right. But actually, all this, picture can be in full. For example, in this part, x greater than 0, or for example, x less than 0. So today we are going to discuss this structure, shock wave and contact wave, and the next lecture will be about the how to compute parameters inside the refraction wave. So what does it mean, and so on. Actually, our second lecture was about scalar conservation laws, And we have already discussed the discontinuous solutions, and we have already obtained parameters called Rankine-Hugoniot jump conditions for discontinuous solutions of scalar conservation law. I'd like to remind you the main results of the second lecture, because the results today will be, just generalization of all the stuff we have already obtained. So there are two actually, different directions in this lecture. So on one hand, as I just explained to you, we need to know how to compute the shock waves, what are the parameters behind the shock wave, to compute numerical flux that can be used in your simulations. On the other hand, the shock wave is interesting and very complex phenomena itself. So in mechanics, in gas dynamics, under some conditions, we can have shock waves, and the mechanics of these objects is very complex and interesting. And so I'd like to explain both, aspects. So on one hand, we should keep in mind that we know how to use these relationships describing shock wave in our numerical flux computation. On the other hand, I'd like to show you the beauty of this phenomenon itself. If we have shock waves, we cannot directly actually apply our conservation Euler equations, because they are written in differential form. And we need to find so-called weak solutions. So weak solution of this equation, the Hopf equation, is any piecewise differentiable function that satisfies the following condition for any choice of contour gamma. It means that the weak solution of this equation is the solution that satisfies the integral form of this equation. And actually there is formal, Green-Gauss formula approach how to transform from one form to another. And for just one scalar conservation law, we obtained the so-called Rankine-Hugoniot jump conditions. So we consider this PP prime trajectory of discontinuity. So suppose we have some discontinuity, and we discussed that in scalar conservation laws there is a mechanisms of gradient catastrophe. It means that as a result of intersection of characteristic lines, which are straight lines, it's possible to get the shock wave. It's the only way how to resolve the situation where we have convergent characteristic lines. So suppose we have this discontinuity which propagates with the velocity d, and u0 and u1 are states. So this is ahead of the discontinuity of shock wave, and this is behind. And so we just discussed that we should use this integral form of our scalar conservation law, and we should apply. We should choose as this contour gamma a prime, b prime, b, and so we specify this general formula for this contour around this discontinuity, and say that a goes to approaches a prime and b approaches b prime, but in such a manner that a prime, b prime should be on this side of our discontinuity, and a b on another side of our discontinuity. And then we say that there is a relationship between x and t, because dx equals d dt. And here t1 and t2 just arbitrarily time instants. And after that we collect everything into one integral, and it should equal 0. And for that the integrand should be 0. And on this way we obtain the relationship between the parameters in front of the shock wave and behind the shock wave in connection with the velocity of our discontinuity d. And actually we can consider this relationship in different manner. For example, we can so usually we do not know the parameter u1. So usually in reality we know parameters in front of the discontinuity. For example, we know parameters here in this room, and we may well, maybe not know, but we would like to know what the parameters behind the shock wave will be if the speed of the shock wave is d, for example. So if we want, so if we know this d, then we can find this u1 from this relationship. This is the usual statement of the problem. What is also important for our lecture is that the same, yes, and we named this, so this formula. We named this formula Rankine-Hugoniot jump conditions. Although Rankine and Hugoniot, they consider gas dynamics, and I will show it later today. But nevertheless, so this is the Rankine-Hugoniot jump condition. So it means that if you have a discontinuity, it's not possible to have some arbitrary parameters to one hand, to one side and another side. They should be this one. And it's possible to use another notation for Rankine-Hugoniot jump conditions. If we use F, our flux, so we can obtain this formula from the previous slide. But after that, we will remind that this U squared over 2 is our flux in the scalar conservation law. And then we should keep it and obtain the Rankine-Hugoniot jump conditions in this form. Actually, this form is universal, and it will be the same for systems, nonlinear systems, linear, nonlinear systems of hyperbolic equations. And for gas dynamics, it will be the same if we will substitute this u by conservative variables vector, and this f, the vector of fluxes. But so this notation is widely used for Rankine-Hugoniot jump conditions. So it says that the fluxes to the left and to the right are connected with the difference of parameters times d, where d is the velocity of the shock wave. So all this was obtained for scalar conservation law, just for one equation. But now we would like do the same things. We'd like to do the same things for Euler equations. For that, we should also use integral form of Euler equations. So I'd like to remind you that actually, for many times we have already written this integral form of Euler equations. So mass conservation, momentum conservation, energy conservation law, and what's very important, entropy inequality. So for this topic, the existence of this entropy inequality is of great importance. And so it's also possible using the same Green-Gauss formula to, this is general form for arbitrary contour L, mass, momentum, and energy conservation laws. And again, we can consider this xt space and choose some contour. And actually, we can do the same thing as we have just done for scalar conservation law. But here we should consider each equation separately. So we have 1, 2, 3 equations, and we should obtain correspondingly 3 jump conditions for mass conservation law, momentum conservation law, and energy conservation law. For example, let's take mass conservation law. The equation, so now we have 3 parameters: density, velocity, and pressure. So within the scope of this lecture, I will use v for velocity, not u, because previously I used v, and now on slides, so it's v. So next time maybe I will change it to u, but so now rho is the density, v is velocity, and p is pressure. Subscript 0 means that these parameters correspond to the space in front of the shock wave, or discontinuity. We don't know what does it mean, shock wave. Some discontinuity, propagating with the velocity d. And the question is how to compute the parameters behind this discontinuity, or the same. So what is the relationship between the parameters with subscript 1, 0, and the velocity of our shock wave? Just in the same manner, we choose this contour and do the same manipulation. And after this manipulation, we obtain the relationship. So rho times v minus d to the left, equals to the same value to the right. And we can do just the same manipulation for momentum conservation law and mass conservation law, and obtain the corresponding jump conditions. So nowadays, these three equations, they are known as Rankine-Hugoniot jump conditions. Often, the following notation is used. So first of all, U variable is introduced. U equals V minus D, relative gas velocity in the reference frame moving with the discontinuity at speed D. If we introduce this relative velocity, then the first equation transfers to rho u in square brackets equals 0, where square brackets notation is used for just the difference between the parameters behind the shock wave or discontinuity and ahead of discontinuity. And so Rankine-Hugoniot jump conditions can be written in this very simple manner. Just the gap, the jump of rho u equals 0. So it means that actually the mass flux through the shock wave should be the same to one side and the other side. And actually, if you look at these expressions from mechanical point of view, that can be obvious, because so this is just mass conservation law. For sure, if you have some max flux, it shouldn't be it should be the same. It should not disappear anywhere. But actually, everything is not so simple, and I enjoy this historical note. It illustrates that people were confusing about this result. So the existence of discontinuities in the state of a gas within a flow has a long time been a controversial subject. So I used this historical note from book Serene. It's an American mathematician, and in this book he provided mathematically rigorous results in fluid mechanics, and so I can recommend this book. I can recommend you this book. But for sure it's a bit difficult, but actually for some topics the results are can be directly applied. The concept of a discontinuity surface and the first two conditions above, I mean this one and this one, are due originally Stokes. So this is the same Stokes who discovered this Dirac law for a body moving in viscous fluid. So the Stokes law, and Stokes' remarks concerning these topics still make interesting reading. So he used these words: "These conclusions certainly seem sufficiently startling, yet a still more extraordinary result. The result, however, is so strange," and so on. So the results are, not usual. So people, for a long time, they were not sure that there exists some, strong discontinuity in parameters in gas. So it was not intuitively, accepted. The thing is that, for sure, in reality, you don't have, infinitely thin structure. So in reality, you have viscosity, and in viscous media, the shock wave is a structure with very sharp changing of parameters, but nevertheless of some certain thickness. And the thickness of the shock wave is about an order of magnitude of 3 mean paths of molecules. And but from a mathematical point of view, if you solve all equations, right, there are no thickness. The fact that energy should be conserved across the shock wave is implicit in investigation of Rankine, and was later given precise form by Hugoniot. So it's the end of 19th century, when separate different works, people derived all these expressions. So in fact, the Rankine-Hugoniot jump conditions state that the jump of mass flux, momentum flux, and energy flux. So these fluxes should be the same to the right and to the left of our discontinuity. So I've written here rho u is not equal to 0 if we want to use this notation, because we want to, you can see here rho 1 v minus d, rho 0 v minus d, and they actually the same. But we can, divide by this factor only if they are not 0. But they can be 0. And what does it mean? So classification of discontinuity surfaces. So these discontinuity surfaces should be classified on the basis of this mass flow through the discontinuity surface. So it should be either 0 or non-zero. If it is 0, so such discontinuity surfaces are called contact waves. So what does it mean, a contact wave? So a contact wave means that it's a discontinuity in gas that separates the two gases with the same velocity and pressure, but these gases can be different and they can have different densities. Why is it so? So suppose m is equal to 0. So if m is equal to 0, densities are not 0, so they are just some physical quantities. It means that V1 equals d and V0 equals d. It means that gas to the left and to the right, they has the same velocity, and this velocity is equal to the velocity of this discontinuity. It means that the velocity can be either 0 or non-zero. So V0 is just the gas at rest. If non-zero, it means that this gas just moves with some velocity. And if V1 equals to V0 equals d, it means that it goes to 0, and P1 equals P0. Okay, and here and here 0. So the last equation is fulfilled, and the densities can be just there is no relationship between ρ1 and ρ0 that can be arbitrary. And so these are contact waves. So, the power of this model of Euler equations, and we obtain these relationships not just from some physical intuition, but actually rigorous enough. The strength of these equations is that all the structures that we are going to discuss today, they exist in reality, and the properties of these objects in reality, they can be predicted well using this model. That is why we study these Euler equations. That is why we use them. That is why they're implemented in all the software. Because on one hand, so this model can be mathematically studied, and the results are mathematically rigorous. On the other hand, the results can be applied in practice. So, but as for discontinuities with m is not equal to 0, so such discontinuities are called shock waves. For shock waves, we have three equations for three unknowns. For example, if we consider the parameters with 0 are known, and for example d is known, then we can answer the questions what the parameters will be behind the shock waves. Then we can resolve this system of equations and find ρ1, v1, and p1. And generally speaking, v1 is not equal to v0 as for pressure and density. So it's a real jump in all the parameters: velocity, pressure, and density. So if you consider the propagating shock wave, then all the parameters, so for example, shock wave that propagates in a medium at rest, it means that the density, pressure, and velocity behind the shock wave will be higher than those in front of the shock wave. Okay, here I'd like to explain some mechanics of this object. So I have already shown you this slide. So the slide I have shown you on the first lecture as the example. So I told you that the flows of motion can be very different. And so there should be motion of incompressible fluid behind a cylinder, and so all the questions of turbulence, for example, and it should be high-speed flow. So the first benefit which the physical scientists repeated from high-speed photography was the visualization of shock waves. So people developed the high-speed photography, so-called Doppler technology, and this Doppler technology, adopting the Schlieren technique devised by Doppler, Ernst Mach, photographed and measured supersonic waves in the wake of rapidly moving projectiles. So why supersonic? We will also prove today that the velocity of propagation of shock wave is supersonic relative to gas in front of the shock wave. And at that time, people just discovered it experimentally. They realized that the body which moves in media should be high speed enough. So it's the speed of this moving body is not high enough, so these structures do not form. so Mach's preliminary experiments in 1884. So actually, you can see that. Interesting to know that at that time people investigated these, effects theoretically and also experimentally. But it looks like in this case, in the 19th century, the experiments, so the simulations were the first. So Mach's preliminary experiments with attached pistol revealed no shock waves on account of subsonic mass velocity. So if the velocity of this bullet is subsonic, no shock waves. And then they undertook experiments with larger projectiles at high velocity and achieved the first photographs by 1886. Mach's theory that the waves should become visible only above the speed of sound, about 343 meters per second in dry air to temperature, proved correct. Last lecture we discussed this speed of sound, and so on last lecture we obtained this. Actually, this expression can be obtained right from rigorous mathematical analysis of Euler equations. So I'd like to remind you that we considered the Jacobian matrix of our Euler equations. Then we computed the eigenvalues of this matrix, and these eigenvalues were u minus c, u and u plus c, where c is some object, and it happened that it turned out that it's the speed of sound. This is the history. In the majority of books, usually the shock waves are of interest from two, points of view. So for sure, this is aerodynamics, and in aerodynamics, usually the so-called stationary shock waves are of interest. So the object that we have discussed, they call also normal shock wave. So the normal shock wave, it means that the shock wave front is perpendicular to the direction of its propagation. Actually, there could be, oblique shock waves and so on. We're not going to discuss it here because it's not the course on aerodynamics. Normal shock waves occurs in a number of practical simulations, such as, for example, in the intakes of engines, in some supersonic aircraft, in the exhaust systems of engines, in long-distance gas pipelines, and in mine shafts, and as a result of the use of explosives. So, when a normal shock wave occurs, for example, in a steady flow through duct, it is stationary with respect to the coordinate system, which is fixed relative to the wall of the duct. Such a shock wave is called a stationary shock wave, since it is not moving relative to the coordinate system used. So, for example, if you have a steady flow around a fixed body, and this flow is high speed enough, supersonic, then we will get stationary shock wave. And in the majority of books, the Rankine-Hugoniot jump conditions are considered for this statement. So they consider profile like V, A, B, and so on with prime here, and they obtained Rankine-Hugoniot jump conditions take into account that the shock wave is stationary. So this is another statement which is closer to me. On the other hand, when a sudden disturbance occurs in the flow, such as the sudden closing of valve in a pipeline or an explosive release of energy at the point in a duct, a normal shock wave can be generated which is moving relative to the duct's walls. So on the other hand, consider the tube and some accident explosion, for example, and then the shock wave will propagate. So I explained to you the shock tube, for example. So this shock wave and this shock wave, so they are actually the same objects, and so they're described by the same equations and so on. But usually in this case, we transfer to the coordinate systems, to the frame attached to the stationary shock, and we believe that shock is stationary. And here we consider the movement shock wave, and so that is why you should be just careful when you read books and realize which situation do they consider in a book. Okay. So for me, this case is more interesting because it relates to my scientific interests at most. C5. Okay. I'd like to provide you several examples from both areas, from this one and from this one. Actually, I enjoy this illustration of of the shock wave. So this is from social media of Professor Higgins from McGill University. He is one of world experts in high-speed compressible flows, combustion, detonations, and shock waves, and so on. So he provided some infographic to explain what was seen in the SpaceX Starship last week. So it was more than 1 year ago. So this is a series of snapshots for different attitudes. So H 100 kilometers, 98 kilometers, and 82 kilometers. So this is the bow wave. So this structure, so this is the body of aircraft, and this red line corresponds to the bow wave. So bow shock wave, it is also called. And the bow wave seen in front of a re-entering spacecraft is where the flow abruptly comes near the rest via shock. But just how abrupt is determined by spacing between molecules, or more precisely the mean free path, MFP denoted lambda. So the problem is for simulations as well. So when your aircraft moves in atmosphere from to the surface of Earth, for example, at high altitudes you're not able to consider your medium to be continuum. So you don't have continuum media. And so in this case you should use not equations, not Euler or Navier-Stokes equations. You should use kinetic theory approach. Then in between region, so that is why this problem is very difficult for simulations, and that is why people still try to develop some universal models that can predict the motion of this aircraft in atmosphere from h equals 100 to the surface. So the red bar here showing the mean free path relative to a schematic of the leading edge of this fin. I mean this structure of the aircraft. So for example, at 100 kilometers, the mean free path is 50 centimeters on the scale of the fin itself. So it means that for this altitude, the mean free paths between molecules is an order of magnitude of some parts of this aircraft. That is why we do not see this as shock wave. We see here some lightning, some red color, but we do not see here any sharp changing of parameters. But when h equals 98, we can see also some smeared structure, but nevertheless. But for 82, we see obvious shock wave. So this is the shock waves as a result of motion of this high-speed body in atmosphere. So on the scale of fin itself, so the shock appears diffusive and spread out. At 82 kilometers, the mean free path is less than a centimeter, so the shock appears crisp and sharp. So it appears here. Here it appears here. And the governing equations and type of computer simulations needed to analyze these two flow regimes are entirely different. So this is also an example that you're unable to take just one software, just one model, and compute everything that you need for your spacecraft applications. So you need, and the problem is that also usually the experts in these models and experts in these models are not the same people. So people usually do either these simulations or these simulations, and nobody knows what to do, something in between, and so on. That's a problem. That the types of models are completely different in these two cases. This is another case. So this case is more close to my field of expertise. So actually it's totally different area, right? But we have also shockwave that on totally different scales, right? You can see here. So it's explosions in the port of Beirut in 2020. So the very famous videos. There are a lot of videos of this incident because there was a series of explosions, and when this burning started, a lot of people started making videos, and there was a sort of deflagration to detonation transition. It means that there was a very slow combustion of this ammonium nitrate. So it was a huge storage of ammonium nitrate, and actually it was used for fertilizer, actually used in agriculture. So that was not about weaponry, it was just fertilizer. But actually this is an explosive, and if something goes wrong, we can get strong explosion. And there are a number of papers in shockwave journal. So the shockwave journal is the main, one of the main journals in the world where people, study this phenomenon. So there were two explosions during the second, more powerful, 2,750 tons of ammonium nitrate. That was a huge disaster, and half of the city was, destroyed totally, and all windows and doors and so on. So they were destroyed, and the parameters of the shock waves was estimated using videos, and it's possible to make a correlation between the propagation of the speed of propagation of velocity and the energy released at the source of this shock wave. And so this is the so I try to provide an example of this effect and of this effect. So in both cases you have shock wave, but here this is a stationary shock wave. When you have a flow around, fixed body, and this is the example of when you have a release of energy and a moving shock wave. But in any case, the Rankine-Hugoniot jump conditions that I will go into to discuss, they are the same, and you should know them. I would like also to show you several examples from my scientific research. For example, particle resolved simulation of square particle motion behind a shock wave. The modeling of dynamics of one or many particles or bodies moving within compressible and compressible media is essential in addressing a wide range of different applications. So if we consider high-speed scenarios, the transport, for example, the transport of coal dust particles during the initial phase of coal dust explosions, the evaluation of hazards associated with debris ejected during incidental detonations, and the dynamic behavior of meteoroid fragments in atmosphere. So it means that in some cases you should know how the complex shaped bodies move in high-speed environment. For example, there coal dust particles or some parts of objects after incidental explosion and detonation. But actually there are a number of civil applications. For example, relevant engineering applications range from supersonic separation technology for carbon capture. And so what does it mean? So one of promising technologies how to diminish the emittance of carbon is the usage of supersonic technology. It means that we can provide micro droplets or even particles of carbon and in supersonic flow, and then capture them, remove from products of combustion of hydrocarbons. And so there are also a number of civil technologies for all these high-speed problems. But for sure, the classical applications are weaponry and some aerospace applications. So the question, we were interested in the studying the dynamics of motion of a square particle in a supersonic flow behind the shock wave. So the statement followed full-scale experiments, and we considered several initial orientations of our particle. So this is a square particle, and this is the incident shock wave. And so previously we discussed how the parameters here and here connected and depend on the velocity of this shock wave. Then this shock wave interacts with the square particle, and we have reflected shock wave and transmitted part. And so this diffraction of the shock wave, interaction in the symmetry axis, and then this reflected shock wave, they interact with walls and so on. And this reflected wall, they form the one primary reflected shock wave, and all transmitted shocks, they form one transmitted shock wave. And so we studied and compared the stability of propagation of this particle depending on the initial orientation. So, for example, here is particle is initially oriented edge on the flow, and here initially oriented diagonal to the flow. And you can see, for example, here the particle moves faster because the cross-sectional area here is greater than here, and so gas exerts its pressure on a higher surface. That is why it moves faster. So a lot of reasonable mechanics, in fact. But so all these structures, they are shock waves. So here we visualize the absolute value of density gradient. And so I explained it on the first lecture. So this visualization and simulation follows the Schlieren techniques in experiments. And for example, this application. Let's continue. And so the last example that I would like to show you is also an example which is full of shock waves. It's a problem about particle lifting from the surface. So actually, this is a classical problem. Again, the field of explosion safety issues, because the mechanism of interaction between a shock wave in air and a layer of fine particles. Yes, it has been studied for more than 50 years, but actually nobody tried to do such simulations using particle resolved approaches. So usually people do it using two-phase flow models, and but my scientific interest was to simulate this process with the consideration of each particle separately. And there are experiments in which people just put one particle on the floor of the shock tube, then produced a shock wave and propagated, and so people studied the motion of this particle in the floor behind the shock wave, and it will move forward and also upward. So they will be lifted. And the question was, what's the influence of the roughness of the flow? And so in the experiments, they considered many particles close to each other, and one or several particles at large distance from one from another. And they compared the dynamics of motion of particle in the vertical direction here and here. And so we analyzed this process, and so the flow propagates from left to right. And so this is a shock wave. It propagated, interacted this particle, and so you can see the reflected disturbance, the reflected wave, and so these are disturbances, these are pressure contours. So the blue color corresponds to lower pressure, and the red color corresponds to high pressure. So you can see this blue color corresponds to parameters in front of the shock wave, and when the shock waves meets the particle, you can see here pressure rise, and so on. And in case of many particles, you can see a lot of reflection waves, and each of this wave actually affects this particle. And we obtain that for during some time interval. So this additional reflected wave, they promotes the lifting of particle, but after that time, so these vortices, they actually it's bad for particle lifting. They work in the opposite direction. So this is another example of problem with many shock waves. Okay. Now let's move towards the analysis of Rankine-Hugoniot jump conditions. So we derived mass, momentum, and energy conservation actually equations across the shock. Suppose that we consider shock waves. Shock waves, it means that this rho v minus d is not equal to 0. Let's introduce this u, a relative velocity v minus d, and eta equals 1 over rho. So the reverse density. Then we introduce these new notations here in the system, and then so the first equation will transfer to this ratio of eta is equal to ratio of relative velocities. Then let's do the following feature. Let's exclude velocities from these first two equations and put them into the energy equation. For that, we should express u1 as a function of u0 and eta, and then put it here in the momentum conservation law. On this way, we will obtain the u sub 0 squared. And then, quite contrary, we express u sub 0 from here, and again put it to the momentum conservation law, and we will obtain u sub 1 squared. So we expressed the velocities as functions of pressure and density, or p and eta. And then we put this u sub 0 squared and u sub 1 squared into the energy conservation law. And so we obtain this equation. So that this equation determines all possible states and states P1, eta 1, which can be reached across a shock wave from the initial state P sub 0, eta sub 0. The locus of these end states is called a Hugoniot curve or Hugoniot adiabat. So it means that, for example, consider the gas at some initial pressure and density, or eta. And all possible states that can reach this gas if any shock wave with any intensity will pass through it, they will be on this Hugoniot adiabat. So the specific parameters P1 and eta 1 they depend on the intensity of the shock wave that will propagate through the gas. Okay, so we can provide the following geometrical interpretation. We can provide the following geometrical interpretation of the Hugoniot adiabat. For that, yeah, important remark. So here, up to now, we didn't specify the any equation of state. So actually here we do not specify what is E1 and E0. And actually all these Rankine-Hugoniot jump conditions are valid for any compressible media. It may be not gas, it may be some, for example, I don't know, melted metal under high pressure applications. So one of applications that I considered was the development of instability on the surface of colliding metal plates. And if the speed of collision is about several hundred meters per second, during the first several microseconds, your metals behave as fluid, as a pseudo fluid. And you can apply the same equations to study the interface boundary. So it's explosion welding process actually. So here there is a state key laboratory of explosion welding. So how to weld two metals, and so this technology actually simulation. So this technology is also based on actually compressible flow models, or at least can be used. But we're interested in gases, right? So that is why let's specify that E of P and eta is P eta over gamma minus 1. So it's the ideal gas equation of state, right? P over rho or over gamma minus 1. If we apply this ideal gas equation of state, we will get the explicit relationship between P and eta. And it turned out that this is a rectangular hyperbola. So this is the curve. So this is a function from school. It's a hyperbola, P over P0, and so this dependence. Moreover, it's rectangular because this hyperbola has two asymptotes. So we can so if eta approaches infinity, then P over P0 approaches this limit, and if the denominator approaches to 0, then eta to eta 0 approach to this value. We can plot this hyperbola, and this is not just sketch. This is the real plot of this hyperbola for gamma equals 1.4, and these are two asymptotes. So this one is vertical asymptote, this one, and this one is horizontal asymptote. The physical meaning of the vertical asymptote is clear. So it means that the existence of vertical asymptote means that the increase in density across a shock wave cannot be arbitrarily great. So we can think that if you will provide stronger and stronger and stronger shock wave, you will provide stronger and stronger compression of your shock wave. But actually, that's true for pressure, but not for densities. So the maximum possible compression factor is rho over rho 0, gamma plus 1 over gamma minus 1. So for example, if we consider monatomic gas with a specific heat ratio of 5 over 3, the ratio equals 4. For the atomic gas, so the ratio equals 6. And that's it. So this is the maximum possible compression rate. So the pressure goes to infinity, but density goes to some specific limit. So this is for vertical asymptote. But the as for horizontal asymptote, there is something strange, because you can see that pressure goes to negative values. And so what does it mean? So because you know, here in gases the pressure cannot be negative. So maybe something. So maybe we made some mistake, but actually no, because as I told to you, we should keep in mind this entropy inequality, right? So Rankine-Hugoniot job conditions, they were based only on mass, momentum, and conservation, and energy conservation laws. And up to this moment, we didn't take into account the entropy inequality. And this is, you know, another great example of what can happen if we do not take into account entropy inequality. If we do not take into account entropy inequality, we can obtain, obviously, you know, incorrect solutions. Okay, let's let's fix this problem by taking into account the entropy inequality. What does it mean, entropy inequality? It means that only processes with delta S greater or equals to 0 are possible. It means that we should add to this space P eta the curve delta S equals 0. So delta S equals 0 is Poisson adiabat. So we have Hugoniot adiabat, the red line. So this red line is the same as previously. And we also add Poisson adiabat, corresponding to the isentropic or adiabatic process. So it's the curve from school. P over rho to gamma equals constant. Okay, and we can say that so P over rho to gamma to one side and another side of shock wave. So this should be the same, and we should also plot this Poisson adiabat. And it turned out that Hugoniot and Poisson's adiabats have a second order contact at this point. So at the initial point, what does it mean, second order contact? It means that if you compute dp over d eta at this point and dp over d eta at this point and the second derivative as well, you will see that they are the same. So it means that this red curve, you know, couples transfers to this blue one very, very smoothly with the same first and second derivative at this point. Not everywhere, but especially at this point. And the second law of thermodynamics states that only processes with delta S greater or equals to 0 are possible. It means that only processes upper than this blue curve are possible. So here the red curve is upper than the blue one. And so this red part of our Hugoniot adiabat is a possible solution. And here, everywhere below this point, the red curve is below the blue line. And it means that all this part contains unphysical solutions. So we should not, you know, think about why do we have negative pressure, so what does it mean? In principle, everything that is below this point, I mean, this red curve is unphysical. So if we will take into account the second thermodynamics law, we should take only this part. Eta is 1 over rho. So it means, and so 1 equals, corresponds to the initial state. And so for all the states here to the left, eta is less than 1. It means that density is greater than initial density. So it means that all these waves are compression shocks. So compression shock means that the shock wave behind which the density is higher than it was initially. And for these bad solutions, density is less than initial density. So it means that these shocks are expansion shocks. So, and this is not a physical solution. And so this result is known in literature as Zemplen's theory. So expansion shocks are forbidden. Expansion shocks are forbidden means that this red curve is forbidden because it lies below the Poisson adiabat curve. Once again, historical note from Serin book. that the entropy should increase across a shock was first pointed out by Zemplen. Actually, it's a Hungarian scientist. Zemplen's remark, which today seems obvious enough, I don't know why, even today it seems obvious enough, is actually far from a triviality. At that time, when his note was published, both Kelvin and Rayleigh were of the opinion that delta S, so once again, this square brackets means S1 minus S0 is the jump of entropy through the discontinuity. So they thought that this S in square brackets equals 0 at the shock surface. They therefore had serious doubts as to the validity of the shock wave hypothesis as a model for the behavior of real gases, since the first three jump conditions are incompatible with the presumed truth of delta S equals 0. So if we would consider that the entropy is continuous across the shock, then the first three equations cannot be valid, and that is why the greatest researchers of the 19th century they were not sure that these jump conditions are valid, and so this type of law exists. Even Stokes accepted this view, since of his 1848 note in the collected papers, the section on shock conditions were purposely omitted. Even Stokes, who obtained the Rankine-Hugoniot jump conditions, so they were not called at that time just jump conditions, he was not sure about the correctness of this of all this stuff, and he did not include these results in some collection of papers. That's it. So this is another great example that in gas dynamics and for compressible flows we should take into account the second thermodynamics law, and it can help to choose the physically relevant, physically correct solutions. Now I'd like to return to numerical part. Right? I have already shown to you what will happen in simulations if we will not take into account entropy inequality. But now we can return to the same issue, but now we have much more knowledge on this topic. And also the reminder of the previous lecture for you to keep it in mind. So the schematic of the second part of previous lecture was as follows. So we started with the current taxonomy scheme for the linear direction equation, right? This is the quasi-linear form, or this is conservation form, and this is the general notation for finite volume scheme, and this is generalization of current taxonomy numerical scheme for finite volume scheme and arbitrary sign of lambda. Then we generalized it for the linear system of hyperbolic equations. So we discussed what does it mean, hyperbolic equations, right? It's the system with first order partial differential equations or system of equations. So all eigenvalues should be real, and the right eigenvectors should form a basis. They should be linearly independently. So consider, for example, we consider this such kind of system. D over dt plus a d over dx equals 0. But here now a is a matrix, but with constant coefficients. And you can see that this formula is just the direct generalization of this one. So this is 1/2 lambda u, but lambda u is the flux. That is why ff. But here we can say only mod lambda. But here we have omega r mod lambda omega l, where omega r and omega l are matrices of left and right eigen vectors of matrix A. And this is because we are not able to apply the current taxonomy numerical scheme directly to the components of vector U. Instead, we should transfer to Riemann invariance. And in Riemann invariance, the system of equations decouples on a set of independent equations, and to each equation we should apply this current taxonomy numerical scheme because lambda is a model of eigenvalue of the system. The eigenvalue can be of different sign. So the main idea and the main problem is that for the system, all lambda can be of different sign. And that is why we are not able to use just the same scheme, because signs can be different. And we applied this scheme for Riemann invariance, and then we transfer to our initial components of U. And that is why we have this combination, omega r model or absolute value of lambda omega L. And after that, we generalize this formula for nonlinear system of hyperbolic equations. So here R was a matrix with constant parameters, and we can put it into flux here. So F is AU, but for the nonlinear case, F depends on U, and U is a known function, and that's the problem. But nevertheless, we can compute Jacobian matrix dF over du A of U, and also this. So we believe that this system is also hyperbolic, and we can build this decomposition, omega R, lambda, omega L. But here, all these matrices, they depend on U. They depend on unknown vector. Anyway, we can propose the generalization of this formula in this view. So this part is the same. And the problem is here, because for linear system of equations, all these matrices have constant coefficients. But in the nonlinear case, that's not true. And we should compute somehow this product on the H between two cells, between M and M plus 1. How to do that? And I explained to you that there are a number of methods, even the methods that we have already discussed for linear direction equation, how to choose this guy in the nonlinear case. And one of the possible choices is so-called row scheme. And so row scheme is an example of scheme that in its original formulation do not take into account the entropy inequality and provide bad results. And so that's a good moment to discuss about this so-called row scheme. So this this lecture is a bit mixed, as I tried to explain to you, that we should consider consider this shock wave from 2 points of view. So on one hand, we're interested in it because we want to build a finite volume scheme. On the other hand, it's just a beautiful mechanical object, and so we should know its properties actually. So the idea was as follows: how to take these matrices. The idea of row is as follows. Let's replace the Jacobian matrix AU, actually nonlinear matrix, by constant Jacobian matrix. So let's substitute it, but not constant, everywhere for all time instance, but locally. I mean that if we need to compute locally the numerical flux at this point between two computational cells, let's do the linearization. Let's substitute this matrix A of U using A tilde of left and right states, which is the function of the data states UL and UR. This is a linear system with constant coefficients locally. For a general hyperbolic system of conservation laws, the row Jacobian matrix is required to satisfy the following principles. And he suggested that, okay, let's locally substitute this nonlinear matrix using linear one, and this linear should with the following requirements: hyperbolicity of the system. So L tilde is required to have real eigenvalues and complete set of linearly dependent right eigenvectors. So an obvious requirement: we should not change the properties of our system. Consistency with the exact Jacobian. A tilde of U and U equals AU. So actually, this definition mimics the consistency definition for finite volume numerical methods. So I didn't explain it to you, but so you can remember. So last time when we discussed finite volume methods, I formulated Lax-Vendor theorem. So for nonlinear systems, Lax equivalence theorem doesn't work. We have Lax-Vendor theorem, and Lax-Vendor theorem states that if you have a convergence for some conservative numerical method, it converges to for some conservative consistent numerical method, it converges to weak solution. But we also discussed that in the presence of shocks, the consistency cannot be defined in the same manner as for smooth solutions. And so this property actually looks like the definition of consistency for finite volume methods. So the numerical flux is consistent with the initial problem, is numerical flux of U and U equals to F of U. So this is just a remark that this requirement is actually the same as for just finite volume methods. And so the most important, the third one, conservation across discontinuity. So let's build the components of this matrix A to be these Rankine-Hugoniot jump conditions to be valid. This one. So you can see it. Looks like this expression. That is why sometimes it is called that Roy numerical scheme. It transmits all waves to shock waves. Actually, that's not true, but nevertheless, there are some reasons for that. And here, following these three requirements, it's possible to find the components of this matrix A. And Rowe solved this problem, and he obtained some averaging procedure for m plus 1/2 to compute this numerical flux. It looks like this one. So actually, these matrices, they depend on velocity, enthalpy, and speed of sound. And so there are three formulas like this one. This is, for example, for velocities. And he proposed this numerical scheme. So actually, this is, it does not mean that this scheme is bad. Actually, it works in many cases. But there are known cases with problems. So today I showed you the SOT test. So the SOT test it's not a test. It was the illustration of self-similar solution. So it's just a known test when you have these densities to the left and to the right. Velocities are 0 to the left and to the right, and the gap of pressure is 10. But this test is more difficult. This test is called modified version of the SOT tests. And here we have the same parameters to the left and to the right for pressure, for density, but we have velocity to the left, non-zero velocity to the left. And for this test, the exact solution looks as follows. So we have a red shock wave propagating to right, we have a contact discontinuity propagating to the right, and the reflection wave. And this row scheme provides so-called shock expansions. So it means that inside this expansion wave, the density or pressure should change continuously. But this point corresponds to the initial location of discontinuity. And we can see the parameters here changes sharply, so abruptly. So this structure is called expansion shock. Expansion shock. So they are forbidden. So the density or pressure cannot change, in such a manner inside a reflection wave. But this numerical scheme, and so I reminded you how can we obtain numerical scheme using the same framework that we have already discussed in previous lecture. But this scheme without fixes, so for sure it's possible to provide some fixes to the scheme to eliminate, to overcome this difficulty and to have good results. But nevertheless, the original version of this Roy scheme provides these reflection shocks. So once again, this is an example of what can happen if we do not take into account the entropy inequality. And by the way, we can also now discuss. So this is the first order scheme. For the first order scheme, you can see these effects. So this is the exact solution, the shock wave, and you can see the smearing of the shock wave. It means that 1, 2, 3, 4, 5, 6, 7, about maybe 10, or it also depends on the how many time steps do you use in your simulation. Smearing of the shock wave, and this is a contact discontinuity. And you can see another feature that is very typical for shock capture methods. You can see that contact discontinuity is smeared much more in comparison with the shock wave. So if here we have 1, 2, 3, 4, 5, 6, 7, 8, or 9. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so on. So in shock smearing, in shock capturing simulations, contact discontinuity are structures that are smeared at most. Actually, we can also discuss here the Rankine-Hugoniot jump conditions and the difference between shock wave and contact discontinuity. So we obtained here, for example, right? So I told to you that discontinuities with m equals 0, they're contact waves, and for m is not equal to 0 shock wave, and for contact waves, velocities are the same, and pressure is continuous across the contact wave, and densities are different. And here I provided you the distributions of pressure and density. And I told you that this is a contact discontinuity. So at contact discontinuity, you have a jump of density, right? But this contact discontinuity still exists here. But this is a pressure. And you don't see any jump in pressure here, because this is a contact discontinuity. And in correct simulations, or if your numerical method is good enough, so it's consistent, stable, and the second law of thermodynamics is valid in your simulations, then you can get all these theoretical things that we just discussed. So here the pressure is so we have a shock wave and we have a jump of pressure, and so these values for pressure for density and this pressure for this value for pressure, their connection with this state in front of the shock wave, they're connected with the velocity of the shock wave using Rankine-Hugoniot jump conditions. So today we discussed how to find these parameters. If you know these parameters and the shock speed, and how to find these parameters. So we discussed the shock waves and contact discontinuities. Next time we are going to discuss refraction waves. And after that, I'm going to discuss with you how to build this exact solution. So if you know parameters to the left and to the right, how to determine this structure will be realized, and how to find all these parameters. So this density, for example, or this pressure, and so on. So, but today we discussed only discontinuous solutions, only shock waves and contact discontinuities. Okay, the last question. Okay, this is also, I enjoy also this picture from my practice. So we computed the propagation of two particles in a supersonic flow. So this is a strong shock wave and a supersonic flow behind the shock wave. So it propagates and particles can move. And they so moved and can interact actually between each other in aerodynamics mean, or actually did collide. And so this is an example of the good simulation result and not very good simulation result. So if you have shock waves, there are known artifacts, bad features in your simulations. For example, so if you're an expert in gas dynamics, you may know that there are a lot of structures, named structures. For example, this is the Mach stem. As a result of it's an axisymmetrical problem, so you can see that below this axis, so it's just the same picture, and it's axisymmetrical. So actually, they are spheres, and so you have the collision of shock waves in the wake of the cylinder, and the Mach stem should forms. And here you have just the wrong picture. So if you would not know about that, you might think that okay, that's a good solution, or well, for example, Fluent or I don't know what provides you with this picture, and so that's it. What can we do that? But that's wrong solution. It's known that skinked Mach stem, this sharp structure, and this bug is known as odd-even decoupling. So if your shock wave propagates, almost planar shock waves propagates along the regular computational mesh, it is known that for some numerical fluxes, the disturbances in vertical directions can develop. And so this is the property of numerical flux. Actually, the problems with entropy inequality. So although, anyway, so you can change and take numerical flux that is free from these problems, to eliminate this problem. And the problem is that here, if you have some problem, you can try to take smaller time step or some, adjusting parameters, but eventually nothing will work. So the only solution to change the numerical flux in this problem will generate this, bad effects, I think. Okay, and the last question is the velocity. So I can remember you that initially, how did we get the Rankine-Hugoniot jump conditions? We expressed u1 and u0 from these two expressions and put them into the last one. And so analyzed this curve in space density and pressure. But so now let's discuss what will happen with the velocity. So we know the relationship between p and eta, and now let's analyze expressions for velocity. For that, we should put eta1 over eta0 to u0 and to 1, and we also should introduce the speed of sound, or we may say not speed of sound, but this. Okay, c squared equals gamma p eta. And eta is 1 over rho, so this is gamma p over rho. And we may say that we know from mechanics that this expression corresponds to speed of sound. And then we can get expressions for relative velocity of gas, relative velocity of the, relative velocity of the shock wave relative to gas motion ahead of wave and behind of wave. Of the shock wave, and consider limits. So what will happen if P1 goes to P0? So it means we consider the shock wave with very, very small amplitude, very weak shock wave. In this case, the pressure behind the shock waves approaches P0, and density behind the shock waves approach to the density ahead of shock wave, and C1 approaches C0. And also it is seen from here that the velocity of the shock wave approaches to speed of sound. So it means that a shock wave of infinitesimal, very small intensity propagates through the gas at the speed of sound. So from analyzing the Rankine-Hugoniot jump conditions, we can get the following result, that the sound is a shock wave with very, very small intensity. I can remember you that on previous lecture, once again, we obtained the speed of sound from formal analysis of our equations. And here, the same quantity is obtained from Rankine-Hugoniot jump conditions with the following interpretation of the results. Let's return to this diagram, P eta. Here, P behind the shock wave is greater than P0, right? And we can consider this expression, u sub 0. And if P1 is greater than P0, so this is greater than 1, it means that u sub 0 over c squared is greater than 1. And at the same time, for this curve, is less than 1. Because here we have P0, P1. And so this result means that shock wave front propagates at supersonic speed relative to the undisturbed medium and at subsonic speed relative to the gas behind the wave. So it means that a shock wave is a structure that propagates with supersonic velocity. And at the same time, with respect to gas behind it, it propagates with subsonic velocity. So if the shock wave propagates in media at rest, so the velocity behind the shock wave will be high. But at the same time, the speed of sound also will be high because of temperature rise. And in total, the speed of shock wave relative to gas behind the shock wave is subsonic. And relative to the gas in front of shock wave, it will be supersonic. That is why it is said that the shock wave is a supersonic disturbance, because that's always true. This is only for physically relevant part corresponding to the compression shocks. So we do not consider this part, right? Because of Zemplen's theorem. Okay, I think actually that's it.